So now we're going to talk about the simplest situation where we have something we want to optimize on a constraint, right? So we're going to try to optimize a quadratic form, right, or figure out the behavior of an extrema from a quadratic form on a linear constraint, right? And the idea is that, well, this is a local picture, right? A linear constraint on a quadratic form is a local picture of a global constrained optimization problem, right? So, in kind of simple terms, often we want, and maybe the global constraint is actually linear itself, right? We want to optimize a function subject to a linear constraint. Right, so maybe price 1 times good 1 plus price 2 times good 2 is equal to income. That's like a simple linear constraint if we say fix the amount of the prices, right? The simplest example is, of course, the linear constraint with quadratic form. So let's suppose we want to optimize q of x 1 x2, right? So we're going to start with two variables and one constraint. Is equal to a11 x1 squared plus 2a12 x1 x2 plus a22 x2 squared, and of course this is equal to x1 x2 times the matrix a11 a12 a12 a22 multiplied by x1 x2 subject to b1 x1 plus b2 x2 is equal to 0. So we've got our quadratic form and we've got a linear constraint, and we want to know, well, how do I optimize this thing? Well, in this case it's actually pretty easy to solve for the system, right? So we're basically going to solve for x1 in terms of x2, and then we just have a function of one variable, right? So this is kind of cute to look at. So suppose, of course, b1 does not equal 0, and without loss of generality, it's not, right? If b1 were 0, then b2 should, if b2's not 0, then we just replace variables, right? We just reorder everything. If they were both 0, then this constraint is meaningless, and so we just want to know the optimization here, and so we ignore that case. Well, we have, right, solving for the linear constraint, we have that x1 then on the constraint space is negative b2 over b1 x2. And substitution yields q of negative b2 over b1 x2 x2. Well, we just plug it all in, right? Well, we'll get a11 b2 squared over b1 squared x2 squared minus 2a12, what is it, b2 over b1 x2 squared plus a22 x2 squared. And since b1 was not 0, of course this all makes sense, and we can simplify, or we can bring in all these terms together, and we get in the numerator a11 b2 squared minus 2a12 b1 b2 plus a22 b2 or b1 squared all over b1 squared. And we have x2 squared. So it's just a simple quadratic function, no linear term, no constant term in terms of x2. And this coefficient determines exactly whether this quadratic form is positive definite, indefinite, or negative definite. Right? So this is now a quadratic form for x2. So there is global min at 0 if and only if right, and a unique global min at 0 if and only if we have a11 b2 squared minus 2a12 b1 b2 plus a22 b1 squared is greater than 0. Right, we know that b12 was already non-zero, and so if I square it, I get something that's positive. So that guy's positive. So all that matters is the sign of this top term, right? And we'll say that Q is positive definite on the constraint set if and only if this occurs. But what's cute is that this is actually the determinant of what's called a bordered matrix. So this is really interesting. This is really interesting. And it's actually the negative sign of this is going to be that determinant. But we have the following theorem that helps us characterize this situation. So if we have Q of x1, x2 is equal to x1, x2, a11, a12, a12, a22 times x1, x2 is positive definite on the constraint set, on the constraint set b1 x1 plus b2 x2 is equal to 0 if and only if this matrix, or the determinant of this matrix, 0, b1, b2, b1, b2, a11, a12, a12, a22. It turns out this is equal to negative that term we saw in the numerator. Let me see here, it's b2 squared minus 2, a12, b1, b2 plus a22 b1 squared. If this thing is less than 0, of course, because the negative, if this guy's positive, right, then that quadratic form was positive definite, and so if the negative of this is less than 0, then we have positive definiteness. So it turns out that these two quantities are equal to each other, and you can actually work that out for yourself. That's actually a good exercise, and I may make you go through. This matrix that we have just seen, this interesting matrix here, is called a bordered matrix, because we border the matrix A with the coefficients from the linear constraint. So now that we've seen the simplest case possible, we want to know exactly what's going to happen when we generalize, and we'll talk about that in the next video. And it gets a little bit more complicated, but not too much more complicated.